everyone. So thank you all for being here. My name is Lynn. And so the SENECA Association with today's Swedish Astronomical Society meeting is a network. It stands for the Swedish Network for Early Career Astronomers, which is a network that is organized both by and for early career astronomers, meaning basically PhD students and postdocs, those researchers that are at the very earliest stages of their career in research. And these roles are often filled by international researchers. As part of the gig, we sort of travel around and move to different universities, which means that this group of people is generally international and English speaking. Which means that they don't always learn fluent Swedish in the 1 or 2 years sometimes that they spend here, but we are so excited about their research that we want to share that with you all, which is why we host this event in English. So thank you all for being here today. And so today we have 2 speakers, both PhD students. We have Ivelin Georgiev, who will be speaking to us about rise and shine. What can the first light from the universe tell us about its fundamental nature? And then we'll pass the word over to Svenningsson, who will be talking about a journey from the sun to the earth, how solar activity affects our everyday lives. Then I will pass the word to Ivelin. So please go ahead and share your screen, and the word is yours.
Okay, thank you so much. I hope you can hear me, and I hope now you can see my screen. My name is Ivelin. I'm a PhD student at Stockholms University, and I wittingly named my title Rise and Shine. What can the first light of the universe tell us about its fundamental nature? Now, I named it, can you see this? I hope you can see behind this Zoom feature, but I called it Rise and Shine because we're looking, I'm looking at the first billion years of the existence of the universe. So the universe is around 13.4 billion years, but unlike this picture, in fact, the first billion is around here. And you can already see by this example, this is on Sala actually, there's a lot of interesting things going on. And I particularly work in this area, in the epoch of cosmic reionization. And the light I want to talk to you comes from this part, as well as from here, from the cosmic microwave background, which is something I'll touch upon later. So, I mentioned cosmic reionization, but you probably wonder what that is. So, within the first billion years of the universe, actually before that, the universe is quite different from what we expect. It's not filled with stars and galaxies, and it's actually a more simplistic place. It's kind of cold. There's primarily hydrogen, helium, lithium, whatever has been made from Big Bang nucleosynthesis, but no heavy elements that we often call metals. And there's no stars and galaxies. However, there is also a different type of matter, dark matter, which is a pressureless, collisionless type of hypothetical particle that we think exists, that, unlike regular matter, formed the cosmic web a bit earlier and sort of dragged all of the matter that we observe today into collapsed structures that we refer to as halos. And it is those structures that form the birthplace of galaxies and stars in the early universe. So in this picture, for example, here's Earth, a sort of slice, and we look back in time and in space, and I'm referring to this point here. And you can see some stars coming to light in a sense. What's sort of cool and interesting is that these stars and galaxies early on will be nothing like the galaxies and the stars that we think of today, because they're not made of the same materials, and they will cool and interact differently. So we actually expect these stars to be very massive, and hence the galaxy is quite different, and they will emit a lot of photons, which are ionizing. And that ionization is something that catches my interest a lot. Why is that the case? Because while the medium between these galaxies is filled with this hydrogen, which is neutral, so a proton and an electron, the light coming from these galaxies will actually kick the electron out, making it ionized. And what's kind of cool about that is that the medium between the galaxies, even though it doesn't sound so intuitive. Even though it's not stars or galaxies, the medium between the galaxies, when it's filled with neutral hydrogen, can actually emit light towards us. And that's the light I was referring to. This is quite fun because it comes from quantum physics. So a proton and an electron possess these qualities called spin. But all you really need to know is that it can either be, let's say, up or down. So an atom of hydrogen can either have two up or up and down. And actually, it's the up and down configuration that's, in a sense, less expensive. So this neutral hydrogen atom would always prefer to eventually just remove one photon and get to this configuration. And it's this type of radiation that, when it's emitted, comes to us and it's observed with radio telescopes on Earth. And also, what's even more fun is that the universe is expanding. And as it expands, it stretches the light. So actually, it starts off as 21 centimeter, but by the time it reaches is more like, let's say, 1.5 to 20 meters. So we can sort of get, hopefully, a sort of movie of how the intergalactic medium goes from filled with neutral hydrogen to missing. And the reason why that's nice is that it will tell us about the stars that have removed the neutral hydrogen. So that's one way to observe them. Another way would be to use the James Webb Telescope and see very far away. But then you also depend on the lines of sight. But these are all complementary probes, and it's what makes it exciting. Here's a sort of real-life example. I wanted to find a picture. So here's a galaxy seen in both optical light, the one we observe, and in 21 centimeter. What you can see at the center is something I have marked out. So here we know that inside there is a supermassive black hole, accreting matter and producing so many ionized photons. And actually, just like the ionized bubbles that I referred before, you can see this little hole here because there's no neutral hydrogen, so this red stuff. But on the other hand, this galaxy is full of it. And you can see that the mere fact that we can see this galaxy now means that the medium between us and it is ionized. While the neutral hydrogen, so let's say these arms here, result in this darkening here, so they hide away the signal. So here's the same slice again, but now it's sort of flattened in a different way. And this is the area that I look in. And what you can notice is that the redness would be the brightness of the signal, of this 21 centimeter signal, while the black spots will be the signal being omitted and missing. So the signal will be quite strong if we were to slice it like a cake early on. But later it will slowly start to disappear until it's gone completely. And we can actually study this with radio telescopes by chopping it down and looking at sort of the variance of that patch of space. To just give you a sort of idea of what telescopes are being built and exist, I personally work with the low frequency array. So we're trying to get image of this observations of this power spectrum, which is our observable. And it looks like this. It's a very nice space. Radio telescopes look quite different from optical ones. And actually, a smaller telescope like this one tells you about bigger parts of the sky. Conversely, you need humongous telescopes, almost like the size of Northern Europe, to observe something far more precise like the galaxy I showed you. And this comes from the way that radio telescopes work. And even though this already probably looks quite impressive, the whole community has band together, working quite hard for first the inception and now the construction of the square kilometer array, which will be a huge telescope being built right now, should have a prototype by the end of the year, which, following its name, will be a square kilometer of these antennas, giving us unprecedented perception into this field and hopefully an indicator of this signal. Without boring you with the maths, what I want to tell you before is that by slicing a patch of sky, as I described before, we can patch in a different sort of frame of reference. It's called Fourier space, but it's the inverse of the physical scale. And we produce this sort of distribution of energy across scales. It evolves with time. A high value of Z is early, and a low value is present time. A value of the neutral fraction of 1 is a neutral universe, and a neutral fraction of 0 is an ionized one. But what you can take from this image is just the idea that a lot of things are going on. The signal is evolving. This patch of the signal is telling us about the largest parts of space, so the cosmic web. This part of space instead tells us about the distribution of dark matter in galaxies. Well, this little bump here tells us about the size of ionized bubbles. And I've been playing around during my thesis trying to understand these things. Now, I've talked a lot about 21 centimeter signal, but there was another probe that I mentioned earlier. And that actually has to do with the cosmic microwave background. To give you a sense of overview, this is sort of the first light we ever observe. At that time, the universe, primarily the matter and the photons, interact together as a fluid, and the light cannot escape this fluid. But as the universe expands and cools, essentially the light can escape around this period of time, and we sort of get the first picture ever. We detected this in 1965, and even though there was some indication of it, it is a fun story. Penzias and Wilson thought that possibly this is just noise due to bird feces and tried to clean it. But the signal remained, and we continued to study it. And you can see we have these really precise, beautiful maps. And even though you see a lot of differences, the differences between them are very small, like 0.0001. So we actually get a very good idea of what the signal is. We have a very good understanding of it, so we know how it would evolve over time. And it's actually traveled from the beginning of the universe to us right now. And that kind of relates to the probe that I want to just quickly tell you about. So as these photons from the early universe travel to us, they're going to interact with the ionized bubbles that I told you about. And the fun thing about what happens inside these ionized bubbles, if you remember, all of the electrons have been kicked out from the neutral hydrogen. They're floating free. They will scatter with the light coming from the signal, and they will imprint features onto this picture. And with a good understanding, we can actually reconstruct a probe, and we can understand like the distribution of energy. So this is just for your visualization, we already have some constraints of this probe. And what's very cool about that is we get a sort of integrated understanding of the average bubbles that have existed in the universe. We sort of use the cosmic microwave background as a backlight. And close to finishing off now, in my second paper of the thesis, I've actually taken this data and potential data of the 21 centimeter signal, and I try to combine both to understand when reionization ended, so Zn, when there was no more neutral hydrogen, and when there was the middle of reionization, when the universe was half neutral and half ionized. And what you can get from this picture is that just using 21 centimeter data tells me about this patch of space, but it's not very precise. The pink color, which is this kinetics Unav-Zildovich effect, this other probe, tells me about this patch of space, but not about much else. But when I combine them, I get a very tight constraint and a good understanding of when the universe reionized. So I hope that was interesting to you. My phone locked, so it didn't allow me to see how much time I had, but I see it's been 12 minutes. I'm happy to conclude here, and I can have some questions if that's okay.
So on that note, then it's time to hand over to Ida, who is joining us from IRF of Uppsala University. And so I pass the word to you.
Yes, thank you so much, Lynn, and thanks for asking me to speak here today. Can you see my title slide?
Yes, we can see it.
Perfect. So I am a PhD student at the Swedish Institute of Space Physics, and our main office is in Kiruna, but I am in the Uppsala office. We perform research and education about our solar system, so we are a bit closer to home. So this includes all of the planets in the solar system and the near-Earth environment and the sun. And I will actually not talk specifically about my own research, but I will give an overview of how what happens at the sun can affect us on Earth. So another term for that is space weather, which you might have heard of. And we will start at the sun, since this is the source of everything that we do here at IRF. The sun consists of charged particles, and where we have energy which is being produced, as you know, through nuclear fusion. So two hydrogen atom nuclei fuse into helium. But also, and maybe more importantly for my research, is the constant flow of charged particles away from the sun. Ions and electrons, and the ions are mostly hydrogen. And this flow of charged particles is called the solar wind. And now space is almost empty, but not quite. We have, in 1 cubic centimeters, we have around 10 particles, 10 protons. We can compare this to the air in the atmosphere, where we have about 10 to the 19 particles. As we said, it's almost empty in space, but even though it's almost empty, these very few particles per cubic centimeters can have a large impact on Earth. And in this movie, we're looking at the solar corona, one of the outer layers of the sun. And we can see that it has a very complicated structure. And these loops that we see come from the sun's magnetic field. And this magnetic field also evolves over time. And it's the structure of this magnetic field that determines what is emitted from the sun. And on the solar surface, we can have large explosions happening, releasing large amounts of energy and radiation. And these can be of different kinds. They can, for example, be solar flares, which are intense emissions of radiation that can reach Earth in just about 8 to 10 minutes. And the other type that I will mention and that we will follow today is the coronal mass ejection, which is a cloud of charged particles spewed out from the sun and that can reach the Earth in a few days. And today we will follow the life of a CME as it travels to Earth. And just to show you, these CMEs are massive, huge things, many, many times larger than the Earth. And in this simulation, we see a CME moving away from the sun. The color is density in this simulation. And the spiral shape shows the normal quiet solar wind, this constant flow of particles away from the sun. They have a speed of about 400 kilometers per second. So still very fast. And the spiral shape is because the sun is rotating. It's almost like the water coming from a water hose. And this is called a Parker spiral. The CME is this high density blob that's moving even faster, about 2,000 kilometers per second. It also expands as it moves outward. And depending on the direction of propagation, it can hit the Earth or it can miss it. And this takes a few days. Now, when a CME actually hits the Earth, they will interact. And the crucial thing here is the Earth's own magnetic field, which is what we call the magnetosphere. And this is illustrated here with blue lines. So the field lines are blue. And since the solar wind consists of charged particles, the magnetosphere is like a shield that will deflect most of the solar wind that hits the planets, so that it will not hit the planet. However, not everything is deflected, and the solar wind, or even stronger, the CME, can actually load the magnetosphere with charged particles and energy, through a complicated process that we will not go into details about, called magnetic reconnection. Magnetic reconnection allows solar wind particles to enter the Earth's magnetosphere. It also changes the topology of the magnetosphere, which we see in this bending and reconnecting of the field lines. And in the end, these processes will affect the current systems in the upper atmosphere of the Earth, and we can get high energy electrons raining into the atmosphere. And I will start with the nice effects of this. So these electrons that rain into the atmosphere, they collide with atoms and put them into an excited atomic state. And as these atoms then relax, they will emit light. This is what we know as aurora, and the color will be different depending on which element and which atomic transition is causing the emission. And this movie that we're seeing actually shows aurora australis, the southern light. So it's being emitted in the southern hemisphere, and it was filmed by the International Space Station. Now, aurora was one of the first methods for humans to study space and the solar activity, and dating all the way back thousands of years. And auroral emissions are still used today to study the magnetic field and the current systems around the Earth. And they can happen at any time. It's not specific to CMEs, but if there is an explosion of the sun, if a CME has hit the Earth, we usually get stronger auroral emissions, and they can reach even further south. And nowadays, we are still amazed and curious to better understand these emissions. But in addition, in today's society, these processes causing aurora can actually lead to problems with the technology that we rely on every day. So these variable conditions of the sun and in the space environment and their influence on human technology and life, this is called space weather. And some of the effects are summarized here by the European Space Agency. And if we just highlight selected 3 of them, one example is that these changing currents around the Earth, and these currents are in the ionosphere, so upper atmosphere, they can induce currents in our power systems, which can cause anything from signal errors and false alarm triggers to blackouts or damages to the power grid system. And just like with auroras, Sweden is more exposed to this than other countries because we are so far north. And Sweden also has a lot of research in this because of that. Another example is that astronauts can be exposed to radiation during solar eruptions. We can also experience increased ionization in the upper atmosphere, which affects the propagation of GPS signals. So the navigation systems become less reliable. And luckily, the most severe space weather effects are also the rarest ones. But we still need to get better at understanding the solar activity, such as coronal mass ejections, CMEs, and not the least to predict when they will hit Earth so that we can take precautions, maybe not send out our astronauts on spacewalks, or have an explanation as to why our GPS isn't working as well as it should. So what many space scientists actually do is to study in situ measurements of the solar wind and other space environments. And there are numerous scientific spacecraft orbiting the sun and the Earth and other planets, each carrying a variety of instruments. But some of the things that we measure are electric and magnetic fields and properties of the ions and electrons, for example, density, number of particles, and velocity, how fast the particles are moving. And we also have optical cameras, for example, to take photos of the sun. These curves show how some of these quantities, so magnetic field, density, and velocity, change when the solar wind reaches the Earth's magnetosphere. More specifically, a transition from the solar wind through the bow shock, if you have heard of that. Okay, I have time to quickly mention the solar cycle. So the solar activity is just like regular weather. This comes and goes in season. And the solar activity has a cycle of about 11 years. So every 11th year, we are in a solar maximum, where the chances of getting aurora are higher. We have the CMEs and other solar eruptions become more common. And we are actually currently going into a solar maximum. So this is why you've probably heard in the news that aurora are being more and more common nowadays. So I will end this on a happy note with some nice aurora photographs by yours truly. And I am happy to take any questions. Thank you.